So in number 63, we've got a puck, and we're given its mass and original distance, and it moves with that speed. The string is pulled downward, and on a frictionless table, determine the work done on the puck. Hint, consider the change in kinetic energy of the puck. And I gave you again the formula for kinetic energy. What is this problem? Well, it is actually to figure out its final velocity over here. We know the initial velocity here is 0.8 meters per second squared. But what's going to happen as we pull this thing inward? Well, it should speed up. And you might say, well, wait, why? Well, we have to consider the conservation of angular momentum. And in this case, we're trying to figure out what is this velocity over here. Angular momentum, remember, the special case for just a single point moving is just mvr. We can actually figure out the angular momentum beforehand. I'm converting, by the way, the 80 centimeters per second into meters per second because we have to eventually work here in joules. And I'm converting the radius from 40 centimeters to 0.4 meters. So those are our two numbers here. We can figure out the angular momentum beforehand is this number. What does that mean? Well, we know the angular momentum afterwards has to be the same quantity. The only difference is now this. Since we pulled this string downward 15 centimeters, what's happening? Well, the radius has shrunk. Before it was 40 centimeters, now it should be just 25 centimeters or 0.25 meters. Mass of the puck stays the same, and we can very quickly calculate its velocity. Its velocity afterwards is going to be 1.28 meters per second. We're not done yet with this problem. We have to actually figure out the work done on the puck. And they give you a hint, consider the change in kinetic energy. Well, what's the kinetic energy beforehand? Well, 1/2 mv squared gives us that. Or this. Please, purely accidental this time, that the magnitude of the angular momentum matches the magnitude of the kinetic energy. There is no connection. An accidental match. The kinetic energy afterwards does not have to be the same. And if we plug in the velocity we just found here, you'll discover the kinetic energy afterwards is this. It's more than what we started. Why? Pulling down on there, we actually had to do work. We had to exert a force. We actually had to pull down on it for a distance. How much work did we do? Well, we know initial energy plus work equals final energy. In this case, the initial energy was 0.0384 joules from right here. The final energy was here. That shows up there. And the work done in this case, about 0.06 joules. I went to 3 sig figs. 0.0599 joules of work. Yes, it's positive. The system gained energy.